So in this video, we're going to look at three modular exponentiation methods for exponent towers. These sort of questions are very common in public key cryptography and stuff like that. Just a quick word on exponent tower. When you have a to the power of b to the power of c, it is calculated with the bracket there, which means the numbers are astonishingly large. It's not calculated that way. The standard is this way. Okay, so we've got three questions here. Question 1, what is 5 to the power of 5 to the power of 5 mod 23? Question 2, what's the remainder when 2 to the power of 2 to the power of 2 to the 24 is divided by 9? And question 3, what is 12 to the power of 13 to the power of 14 mod 17? And we're going to do three different methods to solve each one. So let's go straight on. There's question 1. 5 to the 5 to the 5 mod 23. Okay, well this method we'll call it the break into pieces method, if you like, and what we do is we break it into smaller pieces. So if we look at 5 to the power of 5 to the power of 5, we could write that as, well, that is obviously equal to 5 to the power of 5 times 5 times 5 times 5 times 5. That's what 5 to the power of 5 is. And that we could rewrite as 5 to the 5 times 5 to the power of 5 times 5 to the power of 5. And if we call this bit here A, and then this bit here B, and then the final bit C, what we're going to do is we are first of all going to work out what this is, mod 23, and then once we've got that answer, we're going to work out what B is, mod 23, and then we're finally going to work out what the whole thing is, mod 23. Okay, so first of all, let's look at this bit, 5 to the power of 5 times 5. So 5 to the power of 5 times 5, which is equal to 5 to the power of 25. We're going to use Fermat's little theorem here, where because 23 is a prime number, and whenever you've got to do something modulo prime, then you should always be looking at Fermat's little theorem. By Fermat's little theorem, because it's prime, 5 to the power of 23 is the same as 5 mod 23. And therefore we can write 5 to the power of 25 as 125, which is 5 cubed, 5 times 5 times 5 mod 23, and that just by dividing by 23 and getting the remainder is 10 mod 23. So the A bit here, mod 23, is 10. So what we do is we put 10 into here, and so B, that's A, that's the A bit. B, we put 10 to the power of 5 times 5, which is just having put 10 into there. Okay, so 10 to the power of 5 times 5 is clearly 10 to the power of 25. Now that equals 10 times 10 times 10 times 10, for the same reason that 10 to the power of 23 is the same as 10 mod 23 by Fermat's little theorem. So therefore we could actually, I could just expand 10 to the 23 times 10 times 10, which equals 10 times 10 times 10 because of Fermat's little theorem, mod 23, which equals 1000 mod 23, and 1000 divided by 23, if we do that, we get 43, remainder 11. Okay, so that equals 11 mod 23. Okay, so we've done the A bit and we've done the B bit. So now what we've got to do is in the whole of here we put 11, and so C, now all we've got to do is do 11 to the power of 5, which is this last exponent here. So 11 to the power of 5 we've got to do mod 23. That's what we want, and that will give us our answer because we've broken it into pieces. Well, 11 squared is 121, which equals 6 mod 23. So therefore 11 to the 4 is 36 mod 23, which equals 13 mod 23, and therefore 11 to the 5, which is what we want, is 143, which equals 5 mod 23, and therefore our answer, 5 to the power of 5 to the power of 5, is equal to 5 mod 23. That is our answer, and we're using the break into little pieces method. Okay, so that's question number 1. Let's have a look at question number 2 now. Here's question number 2. It's exactly the same. What's the remainder when 2 to the power of 2 to the power of 2024 is divided by 9. This number is huge. It's far bigger than the number of atoms in the universe. Now, what we're going to do here is, well, first of all, that's not prime, so we can't use Fermat's little theorem, not that we're going to anyway. But what we're going to do is if we could get this here into the form 2 to the 3k add L, where L is either 0, 1 or 2, well, if we could do that, well, that would be the same as 2 to the 3k times 2 to the L, which is the same as 2 cubed to the power of k times 2 to the L, and 2 to the L, of course, will be a very small number, which is the same as 8 to the power of k times 2 to the L. And then when we did that modulo 9, that would be equal to minus 1 to the k times 2 to the L mod 9. And all of a sudden, we have a very small number. So that's what we're going to try and do. Okay, so what we need to do is we need to get the exponent. Now, the exponent is 2 to the power of 2024. We need to find out what that is, mod 3, so that we can put it into the form 3k plus L. That's the form we want to put it into. Okay, so now basically, well, this is actually quite simple because that equals mod 3. Well, 2 is minus 1 mod 3 to the power of 2024. Mod 3 and minus 1 to an even power is just equal to 1. So that equals 1 mod 3. So that actually wasn't very difficult at all. So we can rewrite 2 to the 2024 as 3 times some k add 1. And now that makes life a lot easier because we can now have a look at this and we can rewrite it just as we wanted to as 2 to the power of 3k plus 1. Admittedly, 3k is large, and just like we said here, that equals 8 to the power of k times by 2 to the power of 1, which is 2. And when we take that, which equals minus 1 to the k times 2 mod 9, because 8 mod 9 is minus 1. Now, looking at this here, this is an even number, 2 to the power of 2 to 2024, obviously. This is an odd number, so this must be an odd number as well, and the only way that can be an odd number is if k is an odd number. So we know that k is odd, and so therefore we know that this equals minus 1 to any odd power is minus 1, so that's minus 2 mod 9, which is the same thing as 7 mod 9, and so therefore 2 to the power of 2 to the power of 2024 is equal to 7 mod 9. That's the second method. I haven't really got a name for that, but it's a very good method for basically sorting this thing out here into a very simple form, which then makes it very nice and neat. Okay, that's question number 2. Finally, question number 3. Okay, 12 to the power of 13 to the power of 14 mod 17. So anyone wants to have a go at that, I'll just pause the video. Okay, now again, we can use Fermat's little theorem because 17 is a prime number, so therefore we know, for the reasons that we've already discussed, 12 to the power of 16 equals 1 mod 17, and 12 to the power of 17 is 12 mod 17. Both of those are Fermat's little theorem. So what we want to do is, if we could get this thing here, 12 to the power of 13 to the power of 14, if we could get it into the form 12 to the 16k plus 11, well, then what we could do is we could say, well, that's 12 to the 16k times 12 to the L, sorry, not plus 11, plus L, and that is the same as 1 times 12 to the L, because of Fermat's little theorem. Well, 12 to the power of 16, that would be mod 17, because 12 to the 16k mod 17 by Fermat's little theorem is 1. And what 12 to the power of L is far, far easier to deal with than 12 to the power of 13 to the power of 14. So what we need to do first is find 13 to the power of 14 mod 16 so that we can write it in this form here. Okay, well, 13 to the power of 14 mod 16. All right, well, let's start with 13 squared is 169, which equals 9 mod 16. Okay, that's a good start. 13 to the 4, therefore, is 9 times 9 mod 16, which is 81 mod 16, which equals 1 mod 16. Ah, brilliant. That makes things a lot easier. So therefore, 13 to the power of 8 also equals 1 mod 16, and therefore 13 to the 12 equals 1 mod 16, and 13 to the 14, which is 13 to the 12 times 13 squared, therefore equals 9 mod 16. So we can rewrite 13 to the power of 14 as 16 times some k add 9, which is the remainder here. Now with that we can stick that up here, and that gives us 12 to the power of 16k plus 9 for some k, and we know, we've already worked out by Fermat's little theorem, that 12 to the power of 16 is equal to 1 mod 17, and so therefore 12 to the 16k plus 9 is equal to 12 to the 9 mod 17 by Fermat's little theorem there. And now this is quite simple, so we got all we need to do is work out what 12 to the 9 is. Well, 12 squared is 144, which equals 8 mod 17. So 12 to the 4 is 8 times 8, which is 64 mod 17, which equals 13. And therefore 12 to the 8 is 13 times 13, which is 169, which is 16 mod 17, sorry. And then 12 to the 9, which is actually what we want. We want 12 to the 9, so 12 to the 9, the final one, is 16 times 12, which is 5 mod 17, and therefore we have our answer. So 12 to the power of 13 to the power of 14 is equal to 5 mod 17. So hopefully you found these three methods useful. They're three different methods. If there is a prime number, you certainly want to take advantage of Fermat's little theorem, and you do definitely want to try and get these exponent towers into some form like this. And then the first one, of course, well, the second one, and the first one, sorry, was slightly different in that that one we just had to break it into little pieces. Okay, well look, I hope you found these useful. If you have, then please like this video and subscribe to the Grusty Academy YouTube channel.